So, welcome to this discussion further on the concept of sampling. Right? We had introduced the idea of sampling in the previous lecture. What was sampling? Sampling simply meant looking at a continuous time signal only at specified points. That is what sampling meant, right? What specified points? Well, there were two options. One could either space the points uniformly or non-uniformly. We chose to space the points uniformly in the process of sampling, because we said that unless we have a good reason to place them non-uniformly, it would be easier for us to carry out an analysis or carry out a study of the effect of sampling when the spacing was uniform. Now, today we look further at the effect of sampling and at the most important question that we had raised in the previous lecture, namely, can we reconstruct a signal from its samples? The whole issue is, there is nothing, sampling seems to be a one-way process, seems to be on the surface, right? A one-way in the sense that there could be several continuous time signals which give you the same samples at the same points. But how do we choose precisely that one of them which is our signal, quote unquote, okay? And what is the information that we need, or what is the restriction that we need to put? Of course, we need to put a restriction. We saw last time that in the absence of restriction, there is, as I said, not only an infinity even greater than the infinity of reals, of signals that passes through the same samples, the same points. So, to narrow down from that large infinity of signals to that one signal means that there must be some constraint put on the signal. And we were trying to build up those constraints one by one, all right. We started with a very severe constraint, that the signal form was known. You see, when the signal form is known, what we mean by signal form is a precise closed form expression for the signal. We saw examples of that last time. We said that the signal is a polynomial of finite degree. A finite number of samples is sufficient to reconstruct the signal. In particular, if the signal were a polynomial of degree p, p plus 1 samples properly chosen would be sufficient to reconstruct the signal. On the other hand, if the signal were a sine wave of known frequency, then there were only two parameters to be determined in the signal, the amplitude and the phase, for which one could choose the values of the signal at two properly located points and obtain the amplitude and phase. Similarly, if the signal had a finite number of sine waves, for example, if the signal had 10 sine waves, there again there is the possibility of known frequency and unknown frequency, right? If the frequencies are all known, then we are talking about 20 parameters, because each of the sine waves would contribute an amplitude and a phase, right? So, we have 20 independent parameters to determine, and therefore, in principle, one can obtain those values, one can obtain those parameters by looking at 20 properly chosen points, getting 20 independent equations on the 20 unknowns, right, and so on. One can keep carrying this further. Now, we extend this argument further. We have been looking at the Fourier transform for quite a while, and we have been giving it an interpretation, right, in various contexts. Now, we look for one more interpretation. You see, the Fourier transform brings very clearly into light the fact that there may or may not be an upper limit on the sine waves that you need to construct a signal. What I mean by that is the following. Let us look at the spectrum. Let a continuous time signal xt have the spectrum or the Fourier transform given by xf. Now, for simplicity, we shall of course assume the signal is real for the moment, right? I mean, it is not very difficult later to generalize to complex signals, but for the moment to be, in tune with what we normally deal with, let's assume xt is real and therefore xf is conjugate symmetric. And we shall look therefore only at the positive side of the f axis. The negative side can be constructed from the positive side, right? The amplitude, the magnitude of the negative side would be an even function. I mean, the magnitude is an even function of f, and the phase is an odd function of f, right? So if I look at the response on the positive side, I am quite contented. Now, there are two possibilities. Either the spectrum becomes non-zero after a point. So, for example, there could be a point, let's call it FB. Right? I've just drawn some spectrum here. Either there could be a point FB, so that xf is equal to 0 for all f, or for all mod f greater than fb. Why am I writing mod f? Because the signal is real, so the same thing will happen on the negative side, right? Either they can exist a finite, so of course fb is less than infinity. That's what we assume. Either this can be the case or this is not the case. There are only two possibilities, right? Now, if this is the case, we call the signal band limited. If this is the case, we call the signal band limited, right? What do we mean by band limited? What do we mean by band? Here, band refers to band of frequencies. Band limited means there is an upper limit on the frequencies that are present, which combine together to form the signal in question, the signal xt in question. You notice that we have considerably weakened our assumption. We are now allowing a very broad class of signals, because I am completely, even if I have fixed FB, I am still completely at liberty to choose the spectrum in between 0 and FP. The spectrum is a complex function of f. So I have complete liberty to choose the spectrum between 0 and FB. What is further is that now we have not a finite number, but an infinite number of frequencies. And there again, it's not just a discrete infinity, it's a continuous infinity. Even though FB is finite, there is still a continuous infinity of points between 0 and FB. So it's a very wide class of signals that we are talking about. And it turns out that this is the class that is most important in most discussions or in most analysis in the context of signal processing, the context of a band limited signal. Maybe I should mention as an aside or as an addendum that band limitedness again is often a bit of an approximation in reality. So, when we say a signal is band limited, we normally mean that most of the energy in the signal for a finite energy signal is confined to a certain band. And when we say most, we decide on a certain percentage. So, it is normally the case that we might look at, say, 99% of the total energy for a finite energy signal, and then we look at the band in which that 99% of the energy lies, right? And we call the upper limit of that band as the band limit of the signal, all right, or FB that we are talking about here. Now, before we proceed to look at this class of signals in depth, one more point about possibilities must be brought out. Either the spectrum could be non-zero in an entire range from 0 to FP, or it might be non-zero in a range starting from a lower limit. So, either one could have this situation, or one could have a situation like this. Right? Here, what are we saying? We are saying there is both a lower non-zero and an upper non-zero limit of frequencies in which the signal spectrum is non-zero. Right? So, of course, xf is 0 for all mod f greater than fp. Fp is less than infinity, but there's also, you see, it's also true here. I mean, one must note here we are also talking about a signal for which xf is 0 for all mod f less than fl. Right? Now, technically, this signal is also called band limited. In fact, one can also, refer to it as band limited with, you see, we call this frequency fp the cutoff, right? So, we say the cutoff is fb, upper cutoff. Yeah, but here one can also have a lower cutoff. If the lower cutoff is 0 hertz, we call the signal low pass. And if the lower cutoff is an FL greater than 0, we call it a band pass signal. Right? This distinction is important because it can, in a band pass signal, you can sometimes have advantages in your strategy for sampling over a low pass signal. But in the phase of beginning of our discussion of the process of sampling, we shall ignore this distinction of possibilities, because the strategy that we develop for low pass sampling, that means the strategy that we develop if we assume that there is a signal whose spectrum is 0 after a certain FB, irrespective of whether or not it is 0 before FB, will be sufficient for all such signals. It will be sufficient, it may or may not be necessary. Right? So, we shall first develop a sufficient approach to sample signals which are band limited with an upper cutoff which is finite. Let us call that upper cutoff FB. Okay? Now, to that objective, we must first ask a number of related questions. What is it that was impeding our reconstruction of the signal from its samples? The fact that there are multiplicities of signals that can give you the same samples. Let us understand these multiplicities a little better. Right? And if we understand the multiplicities, what I mean by multiplicities is the various possibilities, then we can also understand how to eliminate the possibilities once we have some a priori information. See what I mean? If we realize that the signals giving you these samples at these points are these, then looking at that class, one can come to a decision. No, it's not all those others, it's just this one, right? Based on the fact that this one is the one that satisfies the criteria posed by my a priori information. So, what is the a priori information that I am assuming now? A band limited signal. And in fact, let us assume the band of the signal to be 0 to FB. that we have been discussing all this while. Yeah? So, you see, if you look at it now, the question of reconstruction of a signal from its samples becomes a much simpler problem. It can be shown to be equivalent to the reconstruction of a sine wave from its samples. Well, let us look at it this way. What does the Fourier transform tell us? It tells us that the signal is a linear combination of several sine waves. If I can reconstruct all these sine waves properly, preserving their amplitudes and phases, then I can reconstruct the signal perfectly, right? Why should I not be able to reconstruct those sine waves properly from the samples? Well, one way of looking at it is that they may get spoiled or they may get corrupted in the process of sampling. What do we mean by getting corrupted? Well, the signal has a certain spectrum. I know the spectrum is limited to FP. In the process of sampling, I assume that something is going to happen to the spectrum. I mean, perhaps I should be able to interpret this process of sampling in the domain of frequency. And I should be able to interpret the effect of sampling on the spectrum, right? Now, if I can counteract that effect by a describable procedure, I have been able to reconstruct my signal from the samples, right? If I can show that no matter what I do, under certain circumstances, I cannot counteract the effect of that sampling, then it tells me that sampling is irreversible. So, I must look for the conditions under which, given this assumption, I can counteract the effect of sampling and I cannot. All right. So, we first ask ourselves, what is the effect of sampling in the domain of frequency? Right. So, what do we first, let us ask ourselves, what are we doing in the process of sampling in formal language? Yes. So, what are we doing in the process of sampling? Well, if you look at it, let us draw the sampling process here to illustrate what I am trying to get at. What do we mean by sampling? We mean putting impulses. See, okay, let us begin with realistic sampling and then let us go to idealized sampling. Now, what would we do in a realistic sampler? In a realistic sampler, we would have a gating process. You know, a gating process is a process which allows the signal to go through for a certain interval and then stops the signal from going through in the remaining interval. So, let us assume that we gate this signal. What do we mean by gating it? It means that we allow the signal to go through for this period, let us say, and then stop the signal for a period, then again allow the signal to go through for a certain period, stop the signal afterwards, and so on. And you can keep drawing this on either side here. So, this is a gated signal. So, what happens in between, the signal drops to 0. So, one can keep. So, I'll just erase this portion and you can visualize that, the samples have been appropriately the remaining gating intervals have been appropriately drawn, right? Essentially, you may assume that there are two parameters to describe this process. The separation between the beginning of the pulses, let us call it Ts here, right, and the interval of the gating pulse. Let us call it Tp. Now, this process which I have described is called natural sampling. Yeah. This is very doable. This is very doable. I mean, you could set up a circuit in the laboratory to do this. I assume that by now you might have been exposed to the idea of field effect transistors, or transistors that can act as gates. So you could have a field effect transistor whose gate is controlled by a voltage pulse or a gating pulse. When the gate is activated, then the waveform that is fed to the source goes to the drain. And when the gate is deactivated, it stops the waveform at the source and the drain shows a 0 voltage. Right? That's exactly what we are doing here. Right? So this can easily be set up in the laboratory with a combination of operational amplifiers and gating circuits like field effect transistors, and one can obtain a sampled waveform from a continuous waveform. Right? Now we wish to analyze the effect of this process in frequency. What do we expect? You see, we assume that the signal was band limited. Can it remain band limited anymore? If you look at the nature of this, do you think it can remain band limited? Do we still feel it can be band limited? What does intuition suggest to us? Yeah? The sampling is uniform. Yeah, the sampling is uniform. I mean, you're assuming that the interval is Ts between successive beginnings of pulses. So what I'm asking you is whether this gated waveform is still band limited. Yes. Now, what are we assuming about this gated waveform in between the intervals here? See, there are two very troublesome things that we are doing here. You see, one is that you have a sudden drop, right? At the end of every gate pulse, there is a sudden drop. Yeah. Now, no matter how many sine waves you sum, if they are all of finite frequency, you can never get a sudden drop. Think about it. This effect of bringing about a sudden drop in a waveform can never be obtained if you sum up sine waves up to a finite frequency. Yeah, requires a bit of reflection, doesn't it? You see, a sine wave is analytic. A sine wave with a maximum frequency has a maximum slope. What you are asking here is for an infinite slope at a point. And if you sum up sine waves up to a finite frequency, it can never give you an infinite slope. So there's a fundamental problem there. In fact, that's where the problem stems from. And of course, sudden drop and also sudden rise, they are equivalent. I mean, sudden either at the beginning of the gating pulse or at the end of the gating pulse, there is a requirement of infinite slope. So it's very clear that we have lost the band limited nature of our signal in the process of sampling. What does it mean? In other language, we could say we have brought in frequency components. It means now we assume we expect that, if you look at the spectrum, now of course we can find, you see, let's understand. Suppose our signal were initially of finite energy. It is very, very clear that this signal will be of finite energy. In fact, the energy of this signal is going to be less than or equal to the energy of the original signal. So its Fourier transform would exist. Now, if the Fourier transform exists, then it is clear that it can't really be non-zero after a point, right? I mean, what we are doing now is trying to understand the situation intuitively. Later on, we shall build it up analytically, right? But we will first try to understand what's happening. So if the Fourier transform is not non-zero after a point, it means that you have brought in frequency components to achieve the effects of sampling. So what does our task boil down to? The task boils down to seeing whether your original frequency components are hidden somewhere or are present somewhere in the new frequency components. If they are, we can take them out and get back the original signal, because the Fourier transform is invertible. If the original frequency components cannot be retrieved from the sampled waveform, then we are in trouble, right? Now, we need to understand then what is it that can corrupt the original frequency components. So, I think now let us put down this process of natural sampling more formally in a mathematical domain, right? Let us define the following periodic signal. Let us define the following periodic signal. Periodic pulse stream. Let us define the following periodic pulse stream. PT, let us call it PT, right, where PT is equal to PT plus TS for all t. That is the periodicity, right? It is periodic with a period of Ts. Ts is called the sampling period. Pt is equal to 1 by Tp for t between 0 and Tp. And it is equal to 0 for t between Tp and Ts. All right. So it's you know let's sketch this signal. Let's sketch it. And expand the whole. And so on. All right. So, this is periodically repeated. Yeah, this is periodically repeated. What are we doing? We are multiplying the original signal xt by this periodic waveform pt. So, we have the sampled signal, let us call it xst. Yeah, let us call the sampled signal xst. It is simply a product, isn't it? Xt times pt. All right. When we multiply two signals in time, what happens to their Fourier transforms? They get convolved. They get convolved. So now the job before us is to find the Fourier transform. We already know the Fourier transform of xt. We know it's band limited to fb. We know something about it. Now we need to worry about the Fourier transform of pt. What kind of a Fourier transform would pt have? What kind of a signal is PT? Yes, it's a periodic signal. So if it's a periodic signal, what kind of Fourier transform would it have? A train of impulses located at what points? Multiples of the fundamental. And what is that fundamental? 1 by Ts. So we would have a Fourier transform with impulses located at 1 by Ts. Yeah. Now what would those impulse strengths be? They would be equal to the Fourier series coefficients. Right? Let's find the Fourier series coefficients. So we need to find out, you see, we understand this argument. We say that excess f, capital excess f, is the convolution of xf with pf, where pf is the Fourier transform of pt, and we need to find out pf. So we need to find out the Fourier series coefficients of pf, of pt. Let us take in particular the kth Fourier series coefficient, Ck. It is given by integral 1 by Tp e raised to the power minus j k omega s t dt integrated from 0 to Tp, but divided by Ts. Do you agree with me? Yeah, do you agree with me? This is the kth Fourier series coefficient, where omega s of course is defined by 2 pi divided by Ts. Do you agree with me? This is the kth Fourier series coefficient of the waveform Pt. Yeah. Very easy to simplify. Well, we get 1 by TSTP integral 0 to Tp e raised to the power minus j k omega s t dt. Which turns out to be 1 by TSTP e raised to the power minus j k omega s Tp minus 1 divided by minus j k omega s. This is true when k is not equal to 0. And it is equal to 1 by TSTP times Tp when k is equal to 0. Do you agree with me? Yes? Yes, no problem. Let us simplify this expression a little further. In fact, let me rewrite on top of this. So I can rewrite, I can cancel the TP's here and get 1 by Ts here straight away. And here I might extract, you see I have a term of the form e raised to the power minus j theta. I can extract e raised to the power minus j theta by 2 common. And then I shall have, and of course, you know, what I can do is I can take the minus sign, the numerator here. So I have this and I have a plus now. So I will simplify this. So I will simplify the expression on top, right. in the following way. It is 1 by Ts Tp, yeah. I have e raised to the power minus j k omega s Tp by 2 here, yeah, and then 2j sine omega k, you know, just for completeness, I shall introduce a Tp here and a 2 there, and also bring in a 2, say, in fact, now I could, instead of having a 2 here, I could bring the 2 down there. This is what it becomes. So, I have done a bit of rewriting, please check, right, I have done a bit of rewriting. You agree with me? Yeah. It is just to put the expression in a convenient form. Yes, actually we don't, yeah, so I need to take care of this Tp. Now that Tp needs to be removed, right? So I've brought in an additional Tp here, that Tp needs to be removed there. Yeah, is it okay now? Yes? It's fine. So, you know, this must, there is no minus here, you know, this is the expression. So, I think we should just, you know, this is a mess here, so let us write it neatly here. It is 1 by Ts e raised to the power minus j. Now, I will write in terms of f, right. So, jk pi f Tp by Ts times the j cancels, and we have sine pi k Tp by Ts divided by pi k Tp by Ts. For k not equal to 0. Please check the expression. In the exponential there should be no f, you are right, there should be no f here. No, yes, that is right. In fact, there should be no f anywhere, right, pi k Tp by Ts, that is right. There should be no f anywhere. I mean, now am I correct? Please check. Yeah, I have just done a bit of rewriting, you know. Now, you see, if you look at this expression, we can rewrite it in even, you know, in the form of a well-known function, sinc. Is that right? Sinc. So, we know that sinc x is sin pi x by pi x. Yeah. And therefore, we can rewrite this in terms of sinc. We can write as sinc k Tp by Ts. k not equal to 0. And of course, now this also brings into evidence the continuity of the expression, because as k tends towards 0, the sinc function tends to 1, and of course this tends to 1. So this tends to 1 by Ts. So this brings into evidence the continuous nature of the dependence of Ck on k. Yeah. Let's sketch this whole situation. What kind? You see, it's very clear that the Fourier series coefficients now are samples of the sinc function. Right? They're samples of the sinc function. It's very interesting. So we have the sinc function. How does the sinc function look? It's 1 at 0, and it goes to 0 at all the integers. It's a pattern like this. So at all the integers, 1, 2, 3, and so on, it goes to 0. I think it's quite clear from the drawing. Yeah, and we've sampled this. So what are we doing? We are sampling, and of course, this is 1 by, it's related to the sinc function multiplied by 1 by Ts. So this thing has been scaled up by a factor of 1 by Ts. All right? And the sinc function has also been multiplied by a phase factor. We call this a phase factor, because it changes only the phase of the Fourier transform, not the magnitude. This contributes a magnitude of unity. It does not affect. So if I look at the magnitude of Ck, I need not redraw it. Right? I need not redraw. So just to get a feel, this is what, if I ignore, let's ignore this term for the moment. All that it does is to introduce a phase. We'll sketch the remaining term. Yeah, that's what we are doing there. So we get a sample here. Now what about the next k? You see, at k equal to 1, you see, notice that Tp by Ts is a fraction. So we are taking multiples of the fraction less than 1, right? That means we have samples of the sinc function taken at small fractions that are less than 1 and multiples of that point. So for example, suppose Tp by Ts is 1 by 4. That means the gating pulse occupies 1 by 4 of the sampling interval. We shall be taking samples of this function at 1 by 4, 1 by 2, 3 by 4, 1, and so on. Right? It could also be, it may or may not be a rational fraction, in the sense that, you may have a situation where Tp by Ts is not rational. If Tp by Ts is rational, then there will be a certain integer. Suppose Tp by Ts is m by n, where m and n, suppose for example Tp by Ts is say 2 by 7. It really means that in every, in 7 times, you see, if Tp by Ts is 2 by 7 as an example, it really means that 7 times Tp is 2 times Ts, right? So, you would be, so there would be a certain, you would start from, the point 0, and there would be a certain integer up to which there would be an integer number of points in the samples, right? So, there would be a repetition of the pattern of sampling if Tp by Ts is an integer. If Tp by Ts is not an integer, then there would be no repetition of the pattern of sampling in a cycle. Anyway, that's just a point of, it's not a very critical point in this whole discussion, but I thought we should get a clear picture of what kind of Fourier series coefficients we have here, right? Whatever it is, I mean, that's not the critical point. The critical point is that we have a Fourier transform that looks like this. Now we'll simply erase this whole. We agree what the Fourier series coefficients are. We also agree, yes, Harpreet? No, all that I said was, Well, the question is, how do we decide the sampling? We are not deciding any sampling period. All that we are saying is that Tp by Ts is a fraction, less than 1. So you would be to get these coefficients here, you would be sampling this sinc pattern at points which are spaced by less than an integer. Now, what I mean is, if this is a rational number, then you could have a certain integer in which you have a sampling pattern, and this sampling pattern would get repeated, right? If not, you would not have that. That's all. I mean, it's not a very critical point. I don't think we need to go very seriously into it. We just need to realize that essentially the Fourier series coefficients of this waveform, the pulsed waveform, are samples of this sinc pattern in magnitude and modified by this phase. Having realized that, we now just forget about what the actual coefficients are. We simply draw the spectrum in terms of Ck, right? But one thing should be kept in mind, this factor of 1 by Ts here, right? The factor of 1 by Ts needs to be kept in mind. So what is the situation that we have now? We have Pf given by a pattern like this. Right? So we have a train of impulses located at multiples of the fundamental. What is the fundamental? Fs. Fs given by 1 by Ts. Right? And the strengths of the impulses are essentially the samples of that sinc pattern. Yeah? I mean, you can continue the sinc pattern here. Right? What's that? Yeah, this is what I have drawn here. No, it's not mod Ck. You see, the strengths of these impulses will be precisely Ck. So they will be complex strengths. So yeah, what I have drawn here is just a few. You see, I mean, for example, we are sure that there will be at least 2 or 3. Since Tp by Ts is less than 1, in the first lobe of the sinc, you'll be taking more than one sample, right? So the first couple of samples are bound to be non-negative. Yeah, I've drawn the magnitude of the sinc function here. I've just given an illustration of the way in which the magnitudes change as a function of frequency. But you see, as I said, that's not really very critical. I mean, I chose a particular pattern Pt for simplicity. What is critical is that there are impulses located here. And now what is critical is that we are going to convolve our spectrum Xf with this spectrum. Right? We are going to convolve our spectrum Xf with this spectrum. We shall conclude this lecture with just one observation. How can we convolve, or what will be the result of convolution of our original spectrum with this train of impulses? What will be, see, the first thing that we need to realize is you can think of the train of impulses as a sum of many impulses. You can think of it as a sum of an impulse located here, plus an impulse located here, plus an impulse located here, plus an impulse located here. So you could think of it as a sum of an infinite number of impulse functions. Convolution is a linear operation. So the convolution of xf with a sum of many impulse functions is a sum of the convolution of xf with each of those impulse functions. And we shall take up from this point in the next lecture.